Welcome back. Today's goal of this lecture is today I will discuss Hilbert space. In my previous video, I have defined what is the Banach space bounded or linear operator. Today's goal of this lecture is today I will discuss Hilbert space. In my previous video, I have seen what is the Banach space. I have seen in my previous video, Banach space is actually the complete nonlinear space. Today I will see what is the Hilbert space. Actually, vector space is to different operation addition and multiplication by a scalar. And these two operations when acts to vector and result is any scalar. This is the inner product we all of us know. Inner product between two vectors is actually the well-known dot product and norm of a vector is used to length of a vector. Okay? And Hilbert space actually complete inner product space, same like Banach space. Here complete nonlinear space and here complete inner product space. At first just recall what is the inner product space. This is mapping from vector space cross vector space to the any scalar. Scalar is either R or complex number. The property of inner product space is symmetric. That means for all xy belongs to the vector space, inner product xy equal to inner product yx. Second bilinear, inner product alpha x plus beta y comma z equal to alpha times inner product x comma z plus beta times inner product y comma z. Third, inner product itself is norm of x. When I will take int is complex number, then inner product xy conjugate would be inner product yx and inner product x comma alpha x plus beta y is equal to alpha bar inner product xy plus beta bar inner product yz. If these fifth property are satisfied, then we can tell this function is inner product space. I hope my all viewers have understood this in better way. Okay? A Hilbert space is actually complete inner product space. Let H be a Banach space. Banach space means actually complete nonlinear space. And Banach space is actually whose norm, which is complex, is actually generated by an inner product space. We all of us know. Norm is actually induced by an inner product. So, when a space is Banach space, that means complete nonlinear space, means whose norm is generated by an inner product space. Let X be an inner product space and Xn be an sequence which is member of X, then Xn is said to be Cauchy if for all epsilon greater than 0 there exists n naught belongs to natural number such that norm of Xn minus Xm less than epsilon, and this is true for all n m greater than equal to n naught. Here this norm is actually induced norm, which is induced by an inner product. And Hilbert space means this is the complete inner product space. That means every Cauchy sequence here converges, and this is actually the induced norm which is actually induced by an inner product. Now let's see some example of Hilbert space. First, we all of us know every finite dimensional norm space is a complete nonlinear space. So when X is finite dimensional inner product space, then it is always Hilbert space. So if we consider Rn-Cn, then inner product X with Y is defined as summation I equal to 1 to n xi bar yi. This is example of Hilbert space. Product space means we all of us know parallelogram law. In inner product space, always parallelogram law holds, and we all of us know what is the parallelogram law. This is the parallelogram law. So, inner product space induces a norm. So, consequently, every inner product space is a norm-linear space. But every norm-linear space not be a inner product. So, a Banach space is a Hilbert space if and only if parallelogram law holds. Now consider LP space. We all of us know LP space defined as LP, here the norm xp equal to summation I equal to 1 to infinity xi I to the power p to the power 1 over p. Choose one sequence x equal to 1 1 0 0 and another sequence y equal to 1 minus 1 0 0. Consider these both sequence belongs to LP. Then x plus y equal to 2 0 0 0 and x minus y would be 0 2 0 0. Obviously this x plus y and x minus y both belongs to LP. Then norm of xp means 2 to the power 1 over p, which is equal to actually norm of yp. Then norm of x plus y to the yp equal to 2 to the power p over 1 over p, that means this value would be 2 and this value norm of x minus y to the power p equal this value would be 2. Therefore, parallelogram law is norm of x plus y whole square plus norm of x minus y whole square equal to 2 norm of x square plus norm of y square, and norm of x plus y whole square plus norm of y minus y whole square equal to 4 plus 4 equal to 8. 2 times norm of x square plus norm of y square means here 2. Here norm of 2 to the power 1 over p times 2, that means this is, and here whole square, that means this is 2 times 2 over 2 to the power p, and that means this value is equal when p equal to 2. Therefore, LP space is only inner product space when p equal to 2, and when p equal to 2, then this is inner product space, and this inner product space is complete. So LP space is an example of Hilbert space when only p equal to 2. Otherwise this is not be a Hilbert space because this is not inner product space. But LP space is Banach space for all p. Okay, I hope my all viewers have understood this is clearly. A Banach space is Hilbert space if and only if it satisfies the parallelogram law. So Hilbert space always induces a Banach space, but all Banach space not be Hilbert space. Okay, well, our next example of Hilbert space is, next, consider X equal to set of all n cross n complex matrix. Now consider two matrix AB in the space X and defined inner product. We all of us know how look like the inner product in n cross n complex matrix. Here the inner product is defined as trace of AB star and norm is defined as trace of AA star to the power half. This is actually induced norm with respect to this inner product, and this inner product always complete metric space. So with respect to this inner product, n cross n matrix space is actually example of Hilbert space. I hope my all viewers have understood what is actually Hilbert space. Now consider CAB, which is actually set of call continuous function defined on the closed interval AB and define norm equal to maximum t belongs to closed AB absolute value of xt. Clearly CAB with respect to this norm is a non-linear space, but this is not inner product space because this does not satisfy the parallelogram law. Norm of x equal to actually maximum between the interval a to b, maximum of xt, this value is 1, and norm of y maximum between the interval a to b, t minus a, absolute value of t minus a over b minus a. Here we have to find maximum. For this, consider f equal to t minus a over b minus a. Then a prime with respect to t would be 1 minus b minus a, which is greater than 0. And since a prime greater than 0, that means the function is increasing function. So maximum value exists in the interval b. So this value would be, just put the value, this value would be 1. And norm of x plus y would be 2, because here 1 plus t minus a over b minus a. In this function, the maximum value exists at the point b. Norm of x minus y would be, since here subtraction, so minimum value added at the point a, and at the point a the value would be, this value would be 0. So here the value is 1. Therefore norm of x plus y whole square plus norm of x minus y whole square, this value would be 5. And norm of x square plus norm of y square, this value is equal to 2, and 2 not equal to 5. So parallelogram law does not satisfy here. So CAB with respect to this norm is not inner product space, but this is obviously norm space. So this is CAB with respect to this norm is not Hilbert space. Okay. Similarly, CAB with respect to 2 norm is not Hilbert space. Here for short calculation, consider AB equal to minus 1 to 1. For this, consider one sequence of function fn which is defined from minus 1 to 1 to r such that fn t equal to 0 where t belongs to minus 1 to 0, nt when t belongs to 0 to 1 over n, and 1 when t belongs to 1 over n to 1. Obviously, this sequence of function be a Cauchy sequence because fnt, norm of fnt minus fmt with respect to this norm means 2 norm. This is tends to 0. So just calculate it own self. This is very easy type proof. This type of example I have defined in my previous video in sequence of function. Obviously, this is Cauchy sequence, but this does not converges to. This Cauchy sequence does not converges. fnt does not converges to CAB because this sequence of function converges to discontinuous function. So this is does not belongs to CAB. So this Cauchy sequence not be complete. So with respect to this norm, CAB is not a Hilbert space. I hope my all viewers have understood what is actually Hilbert space and example of Hilbert space. Okay? Well, I will stop here. In my next video, I will discuss another topic. But at first, I will highly recommend you, please see today's video with pay attention because this concept actually very important for higher study. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.